Okay, today is the advanced structure theories. Last time we talked about static condensation. The static condensations means that we can condense the stiffness matrix, and to condense the stiffness matrix means that we can reduce the dimension of the stiffness matrix. And the reason why we say it is the static condensations, since the condensations is based on the static conditions. And the static conditions means the conditions, they are related to the force. And also there is another kind of the condensation, which is the condensation. Okay, the kinematic condensations is the okay. Compared to the static condensations, the kinematic condensation means that we can condense the stiffness matrix due to the kinematic conditions. And what is the kinematic conditions? You can say they are the conditions Okay, they are the conditions related to displacement, and compared to the static conditions. The static condition means the conditions, they are related to the force, and the kinematic conditions means the conditions, they are related to the displacement. Okay, so far we talked about the truss problems and also the plane frame problems. And I will give you an example. Sometimes we will neglect the axial deformation of beams. Okay, sometimes we neglect the axial deformations for all elements, and that's the typical assumptions for the traditional structural analysis problems. Most of the time in the when we use the traditional methods to solve the frame problems, usually we will neglect the axial deformations, and also we will neglect the shear deformations. So, for the traditional solution methods, usually we consider only the flexural deformations. The flexural deformation is also called the bending deformations. Okay, that's the usual assumptions about the frame analysis. But right now, I'm introducing you another type of the assumptions. Sometimes we can neglect the axial deformations of some elements. For example, we can neglect the axial deformations only. So in this case, for these simple total frame problems, we need to use 4 nodal points and also we can define three plane frame elements. Right now, the element 1 and the element 3, they are the columns of this structure. The element 2 is the beam of the structures. Okay, so if we neglect the axial deformation of the beam, so it means we will neglect the axial deformation of the element 2 only. So in this case, if we define the x-axis as the horizontal direction and the y direction is the vertical direction, then you can say the U2 is equal to U3. Okay, so that's the since we neglect the axial deformations, so we can get the conclusions. The U2 must be equal to the U3. And also this equations is called the kinematic condition. Okay. If we neglect all the if we neglect the axial deformation for all elements, so in these structures, not only the element 2, we will neglect the axial deformations for all these three elements. So in this case, we can say the U2 is equal to U3. Also, we can say the V1 is equal to V2 is equal to 0. And also V4, V1 is equal to V4 is equal to V3. Okay, so that's the conditions we can get. And all these three equations, or you can say there are totally 5 equations. All these 5 equations, they are the kinematic conditions of these problems. Okay, why we will use different assumptions for different problems? And I will say to neglect the axial deformations for the traditional solution methods, since the traditional method is not so easy to consider the axial deformations, since we will increase the number of the equations, also it will increase the number of the unknowns. The traditional method, usually we just use the hand calculations or some very simple calculators to do the calculations. So it is not so easy to solve the number of equations or and the number of unknowns more than 3. So it is not so easy for hand calculations to solve a set of 4 equations and the 4 unknowns. They are not so easy to solve. So that's the principal reasons why we will neglect the axial deformations for this for the traditional method. Since if we neglect the axial deformations for all these, we can get all these kinematic conditions. So in this case, you can assume the unknowns. The unknowns will be the theta 2 and the theta 3, and either U2 or U3, only one. So to solve these problems, you need only 3 unknowns. So you can solve the problems with 3 equations and the 3 unknowns. But if you neglect the axial deformation for this one, then you will need V2, V3, theta 2, theta 3, plus 1 of the horizontal displacement, you can use either U2 or U3. You must use one. So if you neglect the axial deformation for the beam only, to solve these problems, you need 5 equations with 5 unknowns. Okay, but for most plane frame, if you use the computer and if you develop a program based on the matrix structure analysis, and usually we will assume three unknowns for each joint. So totally, we will have a set of equations, and the set of equations include 12 equations and 12 unknowns. Although 6 of the unknowns, they are the known nodal displacements. So we will treat the boundary conditions by some solution methods. But most of the time, we will use either Berkeley's method or MIT's method. If we use the Berkeley's method or the MIT's method, the number of equations and the number of unknowns will not be changed. So, but it doesn't matter for the computer, since the computer can solve 12 equations with 12 unknowns very, very fast. So you will not feel the time pass, something like this. So if you use the matrix structure analysis, usually we will consider all the deformations. Since if you consider all the deformations, theoretically you can get better solutions. Okay, since you can say for all the real elements, you cannot have the such kind of the axial deformations is equal to 0, something like this. Usually, all elements will have all kinds of the deformations, but they are relatively more important or relatively less important. It is you can say only the which contribute more to the solutions, or one of the deformation contribute. Say they are equal to zeros. Okay, so whenever we say we can neglect the axial deformation, we can neglect the shear deformation. Usually, they are only the simplified assumptions. Okay, so however, so for most the matrix structure analysis, you can say we consider all the deformations, but sometimes we can still consider some kinds of the simplified assumptions. We can say we can whether we can neglect the deformations. Okay, if we compare these two assumptions, why some of the analysis neglect the axial deformation of beam elements only, but consider the axial deformations for the columns. Let's compare the axial deformations between the beams and the columns. Okay. Of course, we are considering the frame analysis. Most of our considerations they are for the buildings and sometimes it's the structures of some other structures, but the building is a typical structures. We need to use a frame. We need to use a frame model to analyze the internal force of the elements, and also we like to know the displacements or deformations of the structures. Okay, so you can say right now we are considering the problems of buildings. If we compare the beams of the building and the columns of the building, if we compare the axial deformations between these two elements, first you can say the applied loadings. Okay, the force related to the axial force in the column, usually they are the vertical loadings. The vertical loadings, usually they are related to the dead load of the structures. Also, they are related to the life load in the structures. And the axial force in the beams, usually they are related to the lateral force for the buildings. The lateral force for the buildings, most of the time we will consider for example, the earthquake loadings or the wind loads of the structures. But if we compare the magnitude of these two types of the loadings, for the vertical loadings, for the earthquake loading, usually they are 0.1 to 0.2 dead load. Okay. Usually the earthquake loadings, they are only 10 to 20% of the dead load of the structures. But if we consider the axial force, we need to consider the dead load, also the life load. Okay, so you can say the force related to the axial force of the columns, usually they are much larger than the loads. They are related to the axial force for the beams. And also you can say the support. Usually we have the fixed support. Okay, so for most building structures, usually we have the fixed supports at the bottom. But for the beam structures, usually we do not have the lateral support. So usually all the nodal points for the especially for the floors above the ground floor. Usually we can see the lateral displacement for all the nodal points. So we do not have the fixed or very rigid supports which will restrain the lateral movement of the nodal points. Also, this one is also the reasons why the axial deformations for the beams, usually they are less than the axial deformations for the columns. Okay, so that's the reasons. Sometimes we will neglect the axial deformations of the beams only. Okay, so let's go back to the previous example problems. Let's say we have a structure like this one. We have 4 nodal points, and we have 3 elements. Okay, if we neglect the axial deformation beam, which is the element 2. Okay, so we will negate the axial deformation of the beam elements. And for these example problems, the beam element is the element 2. So we have the kinematic conditions. U2 is equal to U3. Okay. Then how can we condense the stiffness matrix of the problems based on the kinematic conditions? First, you can form the global K matrix. Usually, the global stiffness matrix of these problems, we need to form a 12 by 12 matrix. Since for the plane frame element, for the plane frame structures, we need 3 degrees of freedom for each nodal point. So the 3 degrees of freedom, they are the u, v, and the theta. So they are the 2 displacements along the x and the y directions. Also, we have the theta, which is the rotation for about the positive z directions. Okay, so we can form a global stiffness matrix and the displacement. In this displacement, we have 2 U2 and the U3. Okay. For usual problems, the U2 and the U3, they are 2 independent degrees of freedom. If we consider the axial deformation of all elements, then the U2 and the U3, they must be 2 independent values for these structures. But right now, if we consider the problems which we like to neglect the axial deformations, then we know the U2 must be equal to the U3. And then you can say okay. Okay, if we use 3 degrees of freedom, probably this one is the 4th column, and the U3 is in the 7th column in the stiffness matrix, and there are there are 12 equations. For example, we have the K14 times U2 and the K17 times U3. And also we have K24 times U2. Okay, so totally we got 12 equations, and all these 12 equations, we have two elements. They are related to the U2 and the U3, and the elements, they are shown in the 4th columns in the stiffness matrix. Also, they are shown in the 7th column in the stiffness matrix. And if we know the U2 is equal to the U3, then we can always combine the stiffness matrix. For example, we can add then okay. Okay, so we can modify the K matrix, and we will add the 7th to the 4th, and neglect this one. So we can get a 12 by 11 column. Okay, so we can always add the elements in the 7th column to the 4th column. Of course, you can say we can add the elements in the 4th column to the 7th column. It doesn't matter. You just choose one of the nodal displacement you like to keep to the last. So you can choose either U4 or U7 as the degree of freedom. We like to keep them in the final results. So we can add the one column to the other column to consider the conditions. Okay, let's take a break here.